Alright, welcome back to a Programming 101. Last time I did a video about kind of assembly language and the stack, where when you're talking about the stack and assembly, it's very important that the computer only runs one command at a time, and they go in linear order. Today we're taking a complete 180 because we're going to be talking about multi-threaded applications. That's just a really long word for we're going to talk about applications that use multiple threads. So here's what we're going to do. I'm going to write a chunk of code that sucks. Okay, this code is bad. Here's the code I'm going to write. Ooh, I'm lagging a little bit. Alright, so we're going to do for int I equals 0. Actually, let's make it I equals 2. Let's start at 3 actually. I less than a million I plus plus. So we're going to do this a million times. We're going to do if is prime I, and if it is prime, we're going to print it out. Ugh. Okay. So now all I need to do is write my prime method, my isPrime method. This wouldn't take too long. Obviously I'm going to be checking if it's a prime number. This is just the setup. I'm not doing any threaded stuff yet. Alright, so public static boolean is prime, takes an integer, and the way we're going to calculate whether it's prime is we're not going to use square root, even though that is the best way to do it. We're actually going to start at half of the number. Actually, it's going to be, all of these are going to be odd, so we're going to go n plus 1 over 2. Let me think. Yes, we'll start a... Yeah, okay, because it's going to go up by 2. Here's what I'm going to do is, it's actually going to be I plus equal 2. So we're going to start at 3, and we're only going to check the odd numbers between 3 and 1 million to check which one of them, how many of them are prime. So this is going to be mymath.isPrime. By default it returns false, and now we have to do the rest of our logic in here. So we have to check if n is prime. So for int start equals, that's actually got to go here, n plus 1 divided by 2, start, let's use I is greater than or equal to 2, I plus plus. Oh, actually, no, it's going to return true down here. It's going to return true by default, and then we have to check if it has any divisors. So, the way you check if it's divisible by this number I is if n modulus I didn't talk about modulus, but modulus is division, except instead of giving you the quotient, it gives you the remainder. So if n is 10 and I is 7, this will give you 3. If n is 10 and I is 3, it will give you 1. Okay, because 10 divided by 3 is 3, but the remainder is 1. There's 1 extra. So if n mod I equals 0, so if you divide n by I and there's no remainder, if it's evenly divisible by this number, return false. And I is going to go down, actually, not up. So we're going to start at half of our input number, because no number is divisible by more than its half. And we're going to go all the way down to the number 2. If n is not divisible by anything between 2 and n divided by 2, then it's prime. So this is our logic. And we should be writing some unit tests, so I think I will do that actually. Actually, my unit test will be to test this from 1 to 100, because it's pretty easy to figure out if a number between 1 and 100 is prime. So 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41. Yeah, these all look prime. Yep, that's correct. Okay, so we know our prime method works, but now we're going to check between 3 and 1 million. And we're going to time how long this takes, because when you're talking about multi-threaded programs, it's usually pretty important that the reason you do multi-threading is to cut down the amount of time it takes. So you can get the time, you can get the time from Java, or from pretty much most machines. Time before equals system dot current time millis. Current time millis returns the number of milliseconds that have passed since midnight January 1st, 1970. They chose that because that's when the first Unix machines, well, that's a little bit before the first Unix machines were active. Okay, so anything that uses, this is called Unix time. Anything that uses Unix time started after January 1st, 1970. January 1st, 1970 is called the epoch. That's when this time started. So we have the amount of time before. We're going to get the time after. So even though these calls are the same, they will return different values as long as at least 1 millisecond has passed. And then we're going to print the amount of time it took. It took no space. And this is going to be time after minus time before milliseconds. What happened? It took, oh, I need a plus. Good. So we're going to count how many, well, no, we're not going to count. We're going to figure out all the prime numbers between 3 and 1 million. Let's see how long it takes. It's printing them all out. And you'll see it's only up to 100,000 right now. So this is going to take quite a while. So we know that it's printing out all the primes. Let me stop it. But system out print line actually takes a lot of time to, I don't actually know why, to write to a print stream apparently takes time. So we're just going to comment this out. We're going to have no logic here, but we are going to run this method. This is the method that's expensive. So I'm running it. It is running now, and we just have to wait for it to finish. And it'll tell me how many milliseconds the whole thing took to count from 3 to 1 million in primes. And what we're going to do, I can actually start writing the rest of my code, is we're going to make a new class called prime thread. And prime thread is going to extend thread. Thread is a class that Java provides that you have to import. What happened? Prime thread extends. Extends thread. It's not making me import it. Does it just come with the language? I guess it comes with the language. Yeah, that thing is still going. It's taking quite a while. So anyway, a thread is what we're going to talk about. When people talk about multi-threaded applications, or when they talk about running something on multiple cores, this is what they mean. So normally when you run a Java program, it runs on one thread, which means it'll do one thing instruction by instruction. Okay, when you run multiple threads, you're running two, the best way to think of it is you're running two different Java programs at the same time. Put at the same time in quotes. Okay, at the same time, because, well, I'll explain it. So all threads have to, it should give me an error. Alright, well I guess not. Public void run. And I have to add the override annotation because thread, the class thread, comes with a method called run. What now? Missing Javadoc? I don't care. So here's how you use a thread. God, this thing is still going. I was not expecting it to take this long. Yeah, it'll tell me how long it took at the end. The reason why it's taking so long is because as this number grows, as the number that we're checking, if it's prime, grows, the number of calculations we have to do in here also grows by half as much. No, actually it's linear, sorry. It's linear. We're checking every single number below half. Oh no, yeah, it is half as much. So when this number is 100, we're only checking 50-some numbers. I think it's like 48 numbers that we're checking, because we're not checking 1, and we're not checking... okay, no, yeah, it's 49 numbers that we're checking. But when it's 1,000,000, we're checking 500,000 numbers. So as this number gets bigger, as this number gets bigger, this function takes longer to run. So even though it gets through the first 10,000 of them pretty quickly, it really slows down. So all threads, the thread object in Java, need to extend this method called run. And I'm just going to mock up, no, maybe I shouldn't while it's running. I mean, it's not going to interrupt the process, but I want to wait until it's done. I'll just get rid of this line. And, you know, I'm going to put these things up here to save space. Well, I'll explain it because I actually don't know how long it's going to take. When you create a thread, you can create it just like any other object. You can give it a constructor, which we will. What is this? Prime thread. And we're going to give it a body. And we're going to give it some parameters. So each prime thread that we create, is going to calculate all the primes between this number and this number. Okay? So we're actually just going to store this. So private int start, private int end. So start equals start value, and end equals end value. We have created our thread. The only thing we have to do is fill in this run method, but it's pretty much going to be the exact same thing that we have in here. Except this is not going to be I equals 3, it's going to be I equals start. And this is not going to be I equals 1,000,000, it's going to be I less than finished. So we'll do that. Equals start, I less than, or equal to end, we'll do it that way. I plus equal to. And these have to be odd numbers. I'm defining that they have to be odd numbers. You could do it differently. You could make it calculate any number. But because we're calculating primes and those can only be odd, I'm going to say that whatever I give these into start and end value, these have to be odd. I will just define it that way. I mean, actually, this one can be even, it won't matter. But this one has to be odd. And then, I don't even need the if. Actually, yeah, I'm going to get rid of the if. See what we got. And it's going to be I. Oh, I guess I do need an if. Oh. My bad. I guess it doesn't. There we go. My math dot is prime. This thing is still going. I should have chosen a smaller number. Maybe I should have chosen like 300,000. We're going to be sitting here for quite a while. I actually have no idea how long this is going to take. I didn't run this before. Let me turn up the music a little bit. Just a little bit. Right. Right. Come on. A little bit right there. That's good. So here's what's going to happen. We're going to create a bunch of prime threads, and we're going to give them different ranges of primes to calculate. Actually, since I don't want this to take forever, I am going to reduce this number. We're going to go to, how about 20,000? That'll be significant. We're going to calculate 200,000 primes. This should take significantly less time to do. Let's skip this one. This one's good. So what we're going to do is we're going to create some threads, and I'm going to create a new method. Actually, let's not do that. Static prime method. So what I'm going to do is, this method is going to be my second main method. And I'm just going to call it in the main method and comment out all this other stuff. Oh, there we go. It took 27,826 milliseconds. So almost 28 seconds, okay? We could run it multiple times just to get a good thing. Actually, let's run it one more time. I'll just comment that down here. It does 27,826 milliseconds. Let's run it one more time, but I have to comment this out. Okay. Because it's not going to be exactly the same amount of time each time. It'll be a little bit different. So I'm going to take a second one. Hello, indentation. This is the indentation that I use. You may use whatever indentation you want. Okay, well, while that runs, I can uncomment this and start coding it. So the prime method is going to use the threaded way. And we're going to create, I guess, 4 threads. Okay, so 27,147 milliseconds, and the average of that is, oops, that's 21. Oh, no, that was right. 147. Here we go. So they're pretty close. The average is like 27,517 or something like that. Actually, it's 14. Somewhere around there. So 27.5 seconds roughly. We'll use this as our benchmark without threading. Okay, this is just running this method that many times. So now I'm going to run my prime method. We're going to create 4 of these things. Thread 1 equal new prime thread. And this one, the reason, well, I'll show you what I'm going to do and then I'll explain it. So we're going to start at the number 3, and we're going to go to the, what was I doing, to 200,000. Well, we know that I'm going to create on thread 4, we're going to go up to 200,000 because we need to hit exactly the same range. But what I'm going to do is, let me just do some quick math in my head. 70. Why on earth the indentation? I like it this way because all of the braces, if it opens a block, it closes a block with the same indent. So it's very easy to see that this for loop is right here. It's very easy to see that this method is right here. See, it's on the same column. This is how I do it. Most people do it this way, where the brace goes on the previous line. Whoops, I got rid of that. And then the closing brace ends where the thing started, like the declaration. I don't like that. I think it's ugly. A lot of people like it. It's really personal preference, or whatever your company tells you to do. My company actually makes me do it the other way, where it's like this. This is how we have coding standards, like most companies do. This is how we have to do it on these outer ones, not on these inner ones. But what I do is I code my way, and then I just hit Alt-Shift-F and it fixes it for me before I commit my code. But anyway, that's why I do the indenting that way. It's because the braces line up if they match. And it's easy for me to see it that way. If you're used to another way, that's totally awesome. I'm going to rename these so I stop getting errors. Alright, so I'm going to do some math real quick. That'll go like that. This one's going to go at 169,999, obviously, right before. Actually, it's 998. We don't want to overlap too much. This is going to go to... actually, I'm going to raise this up a little bit to 175. This is going to be 174,998. And it's going to go 140,000. This is going to go 139,998. And this is going to go to 90,000. This will go from 3 to 9 to right before that, 89998. So I have not picked uniform ranges. This one is 9,000 long. This one is 5,000 long. This one is 3,500 long, and this one is 2,500 long. And the reason I did that is because I know that the longer that these numbers get, this will take longer. So what I'm trying to do is I'm decreasing the range of the higher numbers so that I hope that they will all take about the same amount of time. I'm hoping that. I just kind of did some guesstimation in my head. So I'm going to measure what all 4 of these threads do, like the amount of time that they run. Oh, I didn't actually make them run, did I? Okay, here's what I'm going to do. At the end of the run method, which I'm going to make look like this. At the end of the run method, well, I'm going to count it up here. Start time. I'm going to make each thread tell me how long it took to run. And I'm probably just going to store it. So time equals end time minus start time. Okay, so when these threads complete, I will be able to access and okay, I'll just make a method for it. Okay. So that looks good. We're going to go back here. We're going to time the entire well, not yet. I don't want the construction time to public static void. We're going to start time equals system. We're just timing everything today. We are the time lords. End time equals, yep, and all my code's going to go in between here. So we're going to do thread 1 dot start, and I'm just going to copy this for every other thread. Alright, so now we don't want to do that yet. What we want to do is, oh god, how do you join threads? Wait for the thread to die. Is it not join? I thought it was join to wait until it's done. I think it, I'm pretty sure it is join. Alright, join. Hold on, it's been a while since I've had to do this all in one method. My threads usually run independently and they don't have to wait for other threads. So that's why I'm not used to doing this. For example, I have a game engine that is, it's a card game, it's a trading card game. It implements Magic the Gathering. And when you draw a card, the art does not load immediately. It actually creates a thread to go find the art in the file system, or if you don't have that art, it downloads it from a website. So, you know, for one card, it may take like half a second, right? But if you're loading 100 cards, if you're looking at somebody's deck, for example, waiting for all the art to show up could take over a minute. And so rather than doing that, I have threaded the part of the code that loads the art. So you get a code that's just, or you get a card whose art is just blank, and then it fills itself in when it gets it. But it's been a while since I've had to actually join multiple threads, and I forget how to do it. Let's see. Join waits. Is it? I'm gonna get the Java doc. Come on. Okay, I'll just do this again. What does it say? It waits for this thread to die, so I guess this actually pauses the current running thread. Not thread 1, but it will pause prime method, whatever thread prime method's running on. Okay. So what I actually want to do is, you know what, I don't even have to do this. I'll just add up all the time that it took. That's actually a lot better. I need to surround these by a try-catch, because anytime you use threads in Java, you get the not invocation, concurrent, what is it called? It's the interrupted exception. If a thread is interrupted for any reason, if it's killed prematurely, or something tells it to stop, or something locks it, you could get an interrupted exception, even though I know that's not the case. The Java compiler doesn't know that, so you have to catch it. And so at the end of our code, we're just going to print out a bunch of stuff. Thread 1 took get time taken. We're going to go to the next line. 2, 3, 4. 2, 3, 4. And then we're going to do another total time. Aw, man. I'll do it inline, whatever. Actually, no, I'm going to make it a variable. So it'll fit on the screen, mostly. So this is going to be 2, 3, 4. Alright, so this should run if I put it in the main method. So we're going to do prime method. So this is our second main method, basically, and we're just going to comment this out because we don't need it. So when we were doing it with just one thread, the main method runs on its own thread, we got about 27.5 seconds to do the whole thing. Every number from 3 to 200,000. Let's see how long this one takes. If it doesn't crash. It might take longer than I want it to. There we go. Okay, so thread 1 took the longest at nearly 5 seconds. Wait, that's not right. Also, I spelled thread wrong. Hold on, that doesn't make any sense. Thread, did I not? Start equals start value, end equals end value. That doesn't make any sense. That should, these ones at the end should take longer, not shorter. Let me see what I possibly have done wrong. Uh-oh, looks like I'm gonna have to debug it. Let me run it one more time. Maybe I just didn't save something. Did I do my math wrong? Wait, I have 90,000 results here. I have 40,000 results here. 50,000. I have 35,000 results here. Something's very wrong. The ones at the end are taking way less time. So I equals start. Let me actually do a little bit of debugging. %d, %d. This is going to be a printf. And it's going to have a new line at the end. Let's run this and see what happens. Exception. What happened? Missing, oh, I didn't put the actual values in there. Whoops. So, start, end. Yeah, that should be right. End time minus start time. Okay. No, that one can't be run. Let's run this one. Starting thread with parameters. So it started thread 1 first, then thread 4, then thread 3, then thread 2. Huh. That's really weird. That should not happen. Alright, well let's do it this way then. We're gonna go to 50,000. This is gonna go from 50,001 to 100,000. I'll do it evenly. Let's see if we get something different. 150,000. Oh wait. No, 100,001 to 150,000. And then this is 150.01. Let's see what this does. The numbers the higher up numbers should take way longer. So that's why it's kind of baffling. Now the total time is way bigger. Something is very wrong. Oh, also the total time is calculated wrong, because it's adding all these up, but these are running concurrently. So it's actually just going to be the longest one, which was that one. This is what's more expected. See, when they're all even, thread 1 takes the shortest amount of time because, let me stretch this out a little bit, because the primes that it has to check are smaller. So this loop inside this is it prime, this loop is shorter when the numbers are smaller. This one goes into bigger numbers, so it takes a little longer. This one goes into bigger numbers, so it takes longer, and this one goes into bigger numbers. Oh, wait, that one, and then that one. But thread 4 took... Oh, yeah, no, because these are printed in the opposite order. Well, anyway, I just gave them uniform because for some reason the other one was giving me weird results. So when we ran in one thread, it took 27.5 seconds, but this time it took less than half that time because we split the work into 4 different threads. Now, the question you might be asking yourself, especially if you were here at the beginning, is the computer still, you still only have one CPU. Assuming you're not on multiple cores, you still only have one CPU. How does having more threads speed up your process? How does it speed up your program? And the answer to that is in Control-Alt-Delete. What's going to happen to my screen when I do that? It turns black, I guess? So this is the Control-Alt-Delete on Windows. Mac has something similar. These are all the processes, well, these are not all of them that are running, but these are a lot of them. These are a lot of the processes that are running. You just got here, Sir Waffle Gaming wants to know what's going on. We just wrote a multi-threaded application. I'll show you the code very briefly. It's not too difficult. So first I ran this code. I looped between 3 and 200,000 to look for all the primes. And I calculated, or I timed how long that took. Then I calculated the same primes using threads. And I calculated how long it took, except this one's useless. Get rid of that. And we found out that if you use threads, if you use 4 threads to do this particular loop, the time that it takes total is less than half. So we got a significant time increase by using threads. And I was just about to explain why having more threads makes a difference. So here's a list of the processes that are running on my computer. The way your CPU works is it can only run one instruction at a time. We talked about assembly last time. It can only run one instruction at a time, no matter what, unless you're doing multiple cores, but let's forget about multiple cores. Let's say you have a single CPU core. Your CPU core can run a single instruction at a time. So how is it that you have all these programs running at once? Like I have NetBeans open, I have, Skype window that my friend PM'd me open. I've got my streaming software open. I've got a bunch of stuff open. Clearly this doesn't make sense. But what's actually happening is your computer is so fast, it's actually switching between every single one of these applications every frame. Every time your screen updates, your computer has gone through most, if not all of those processes at least once, and it has done some code on them. Okay, so there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's about 25 here. The highest number of threads you should use for the best times. Well, I'll answer that in a second once I finish this thought. I have roughly 25, imagine these are as threads. These are actually processes, but they're basically threads. I have 25 threads here. When I ran this method, it was a 26th thread. That's good. So, I don't know how to pronounce your name. Is it... I'm not even going to guess. I'm going to guess. Deno Sky... I can't tell if that's an I or an L. I really should not try pronouncing most people's names. But he asks, what's the highest number of threads you should use to be the most efficient? What if you ran 200,000 threads, and Sir Waffle Gaming comes back with, prepare a funeral for your PC is what happens. Fantastic answer. So there are 25 threads here. When I ran this main method, we got one additional thread. It's the Java thread. Actually, I'm going to show you that thread. Okay, we're going to comment out the multi-threaded part. We're just going to run the one thread. I'm going to try to keep this open. I'm going to try to get it open as quickly as I can. Okay, so there's a Java here. That might not be it. See if it goes away when the program finishes. I was looking for Java W. That's usually what runs, but maybe it's just regular Java. Yeah, it's Java. CPU usage is 24%. So this is the calculating threads thing, this Java EXE right here. I know it's kind of small. I don't think I can make it bigger. That's not what she said. No jokes. Okay, so the Java thing went away, and it took 27.8 seconds. Okay? Now we're going to run the prime one, and if I don't know if multiple Java threads appear on the Windows thing, but I can show you them in the debug thing on net. Whoops, wrong button. That one, not the last line. I'm hoping that Windows recognizes different Java threads as different processes, so let's see what happens. It does not. But you'll see my CPU usage is way higher. It was 24% before. It's going between, it spiked up to 60. It looks like it finished 3 of the threads and it's just doing the last one now. And it just finished. Okay, so I'm going to show you this in debug mode, actually. I'm going to run, how do you divide the same work among all of the threads? Okay, that code's down here. What I did was, I made a class that extends thread. Okay, this is how you do multi-threaded in Java. You extend thread. There's a second way you could do it, which is you could implement the runnable interface. It's called runnable. So you could do this too. And this is pretty much the same thing. It's actually, I think I can run this and it will actually work. You can do either one. If you have nothing else to extend thread. Otherwise, go ahead and implement runnable. But you need this method, okay? I'll explain this in a second. I'll go over it because I think you were not here when I explained this. So you make your extends thread. Well, this is not the normal process. Oh, I closed it. Crap. This is not like this is the normal application thing. So it says I only have 6, but this is the number of processes that are visible to me. You might see me opening my start menu. Why is command prompt not on my start menu? That's unacceptable. We're going to pin this guy. Pin to start menu. And we're going to run it. And watch this. Uh-oh. Oh, task list. These are all my actual processes. Let me see if I can stretch this out. Go all the way up. Okay, see, this is way more than 25. These are all the processes that I'm currently running. Okay? It looks like there might be like 40 or 50 here. You can already tell there's way more over here. Because there are spaces between these and the font's smaller too. So yeah, Windows is hiding some of them over here. But there are a lot of processes running at any time. In fact, let me actually, that's going to be a mess. I'm going to have to, you know what, I'm going to try this. I'm going to try this, because I have not actually done this before. I'm going to run the, well, let me explain the prime thread. So I extended thread. I have a constructor that just, I give it the start and the end value, and it remembers them. What's it complaining about? Field end can be final. I don't care. And when you call thread.start, it calls the run method on that thread. Okay, so that's what I'm doing. And over here on my test project, you'll see I create the 4 threads. I have evenly distributed the range from 3 to 200,000. This one got 1 number less. It didn't get the number 1. Because we know that 1 is not prime. And it wouldn't really be that much of a challenge to calculate that anyway. And then we started them, and then we joined them all. Join makes you wait until that thread is completed. And in this case, we know that thread 4 is going to take the longest because these numbers are bigger. Originally, I tried to distribute it so that it was skewed towards the lower threads. Like I tried to put 800,000 here the first time, but we got some really weird results. So I just evenly distributed it. So that's how I did it. But anyway, I'm going to try this because I've never tried it before. What I'm going to do is I'm going to run the Java, and I'm going to bring up the task list on command prompt almost immediately. Alright, so let's see, I mean, it's only going to bring up 1 Java thread. It should. Unfortunately, it doesn't tell me how many things I have. So, okay, there's 1 Java exe down there. There might be more. I don't actually know the internals of how Java creates its threads. I'm pretty sure there should only be 1. Looks like there's just 1. So we're going to wait for that to finish. And we'll see if there's multiple Java threads after, okay, 27 seconds as expected. Now we're going to get these, comment those out. We're going to run it again. We're going to quickly do our task list. See, as you can see, this is actually going slower. It's still only returning one Java, it looks like. Java handles its own threads internally, but it asks, I'm guessing it asks, Windows in this case, it'll ask it for additional priority. Looks like there's only one Java. Okay, so that was a bad example. That actually doesn't work. But I can show you how many threads there are in debug mode. All the Java threads apparently are internal on Windows machines. On other machines, they might be different. So I'm going to debug it at... I guess it doesn't really matter where. What's wrong with my cursor? I'm going to debug it somewhere. It doesn't really matter where. And where is my thread count? Okay, the threads are going to be in the top left. There's only one, this main thread running. We'll wait for it to line breakpoint. What? Not able to submit breakpoint? I don't care. Ugh. I really have to wait. We're just gonna stop it. The method with all the thread stuff. The method. Yeah, I'm gonna go down there. So I'll uncomment this and I'll comment these out. And I'm gonna debug it in here. I don't know if it'll show up real time. I might have to stop on a line breakpoint to see the other threads. Possibly. I'm not actually sure. Here's the method with all the thread stuff in it. So I'm creating 4 different threads with 4 different ranges of numbers. They're evenly distributed. Then I start all of them, and then I wait for them all to finish. In this case, we know that thread 4 is going to take the longest because it has the bigger numbers. And I'm just printing out how long it took each thread to run. This get time taken, each thread measures its own amount of time taken, and it stores it. Alright, so I'm going to run this, and hopefully, where did I debug it? Okay. I'm going to debug it. So it's going to stop immediately because it's got one thread. It's got one thread because we haven't jumped into this other method. So I'm going to hit play, and you'll see there are more threads running now. Now there are 5. The first one finished. Second one finished. I'm looking at the top left up here. 3rd and 4. And it's done. Alright, I'll do it again. I wish I could make the top left bigger. But watch the top left when I hit the play button again, up here where my cursor is. Right now there's only one thread because we're in the main method. Okay, we haven't created all those extra threads. So I'm going to hit play, and watch how many threads there are. Now there are 4 extra. One of them just went away. That was the one that took the least time because it had the lowest numbers. The second one just went away. And those other 2 are just going to go away. There they go. Alright, and we're done. So the threads get created and killed individually as they finish. You wanted to see the prime thread class. Right, so the constructor just sets the start and end values. There might be a bug in here because we tried running this with the numbers skewed, and it was giving us results that it should not have been giving us. So it's possible that this is bugged, but let's see, I equals start, Here's the prime thread like you asked. You know what it probably was? It's probably because, no, the end time should still, it should still store the time taken when, even if I'm waiting for a different thread. So Waffle Gaming wanted to see the prime thread class again. Alright, he's got it. So this is how you do multi-threading. And as you can see in this case, it cut our time roughly in half, right? When we did one thread of calculating prime numbers, it took 27.5 seconds to do 200,000 of them. Actually 100,000 because we're skipping the even numbers. But when we used 4 threads, it took half as much time. And the time that it takes is dependent on a lot of things. It's dependent on how many processes your computer is running. I'm running, I'm running stream software, which is taking up a lot of time. It's almost 20% of my CPU. my Skype is on, and it's taking up way more time than it should, considering there are no windows open. And then I've got some Chrome windows that are taking up space. Probably Spotify is one of them. So my CPU is already working pretty hard. I bet if I stop streaming and run this again, it'll take slightly less time. I'm not going to try that, but that's probably what would happen because my CPU would be spending less time doing these other applications. There would be less other threads running. And I feel like I didn't explain it fully because people were asking questions, but the reason why having more threads makes your program faster is simply because there are more threads for your program than for other programs. So think of the programs that you have running as a ratio. Okay, if I'm running one thread of OBS. This is my stream software. I'm running one thread on OBS. This is in Windows though. If I was running 5 threads of OBS, it would be getting 5 times as much CPU time than all the other threads, because the CPU just goes through every thread, every process it's actually called, if it's an operating system. Your CPU is going through all the processes roughly evenly. Okay, not exactly. They have some tricks to speed up and slow down, which is why operating systems are so fast now. But it's roughly splitting the work between all the processes more or less evenly. So that's why when you create extra threads, your program runs extra fast. It's because you're getting more CPU time. And so now I have explained multi-threading. The next thing I will do is explain how multi-threading is dangerous, which is actually a lot of fun. But I don't usually write bugs. I'm going to write a bug today. Hopefully, if you've been paying a lot of attention, you might be able to see it. I'm going to write it intentionally, and I will probably fail. But let's do it anyway. I'm going to create some new threads, some new thread classes. So this is going to be stack reader thread. Stack reader thread. Okay, we're going to extend thread. I have to get rid of these templates. These are really annoying. And, okay, public stack reader thread. It's going to take a stack of integers. Can I do this? Can I do primitives inside there? I don't think so. Let's see what happens. It's not going to let me... Oh, crap. It's not going to let me do that. I think I have to put an actual object. Yeah, I have to put an object. So we're going to do string. No, we'll do integer. This will make more sense. We're going to store the stack that it's writing to. So you may remember from the last video when I was talking about assembly and the stack, what the stack is. So a stack is just a data structure where you add to the top of it and you take off the top of it. Okay, so the things that were put there first will live the longest. Okay, everything that goes on top of it will leave before it. So it's a last in, first out queue. Let's go equal null so I don't get errors. Okay, so stack equals my stack. Alright, so this constructor takes a stack of integers and it just stores it so it knows what it's going to do. Okay, public void run. When we hit thread start, we're going to run into this method, and I'll fill that in. Actually, I can fill it in now. Now here, yeah, I'll fill it in now. That's the better thing to do. So this is a stack reader. How do I want to do this? Okay, while Okay, here's what I'm going to do. Long start equals system dot current time millis, while system dot current time millis minus start is less than 10,000 milliseconds. So we're going to have this thread run for 10 seconds. Let's fix that. we're going to, if the stack I was looking for has elements, but we'll look for, well, if the stack is not empty, we're gonna system out print line the top item of the stack, which is get, can I do like pop? Pop. Pop takes the top item off the stack and returns it. Okay, so do you understand what the stack reader is going to do? We're going to give it a stack, and it's going to run for 10 seconds. Okay, for those 10 seconds, whenever the stack is not empty, so as long as it has something in it, it will take the top item off, and it will print it out. That's what it's going to do. Okay, now we're going to make another class called stack. Actually, we don't even need to do that. But I'm going to do it anyway, because it'll increase the chance that we'll get a bug. We're going to have a stack writer thread. I'm writing a bug intentionally to explain what not a deadlock, to explain what a race condition is. So the stack writer thread is going to be pretty much the same thing as this, so I'm going to copy it. Yeah. Oops. Stack writer. But instead of popping things on the stack, we're going to go if stack.size is less than 10, we're going to push something onto the stack. And actually, the thing we're going to push onto the stack is just going to go up. Oops, stack.push. Alright, so I'm going to explain, just so we're all clear, what these two classes do. Our stack writer, as long as the stack, for 10 seconds, they're both going to run for 10 seconds. For 10 seconds, if the stack is not, we're going to define this as full. Okay, if it has less than 10 items, we're going to put something on the stack, and the things we put on the stack are just going to be numbers that are increasing. So we're going to put a 0, then a 1, then a 2, etc. And we're going to do that for 10 seconds as long as it has less than 10 things on it. Simultaneously, we're going to have a stack reader that's going to go in, and as long as the stack has something on it, we're going to take the top item off and print it out. So you should expect we're going to see, 1, 2, 3, 4, that's what we should see printed out. So let's run the main method. Oh, yeah, I'll keep the prime there. Why not? Okay, so let's do it. Stack. First we have to create a stack of integers. Stack equals new stack. Import it. What is my import hotkey anyway? I'll fix it later. Come on. I use Eclipse at work and I use NetBeans at home, and some of the hotkeys are different and I haven't changed them. So we have a stack, and it is empty but not null. That's important. It's empty but not null. Stack writer thread writer equals new stack writer thread. We're going to give it the stack, and we're going to do the same thing for the reader. New stack reader. And then we're just going to start both threads. So we're going to start the writer first. What? Did I not extend thread? Stack reader extends thread. I didn't extend thread. I couldn't find the start method. Alright. Dot start. And then we'll do reader dot start. Alright, let's run this and see what happens. We're going to get a lot of numbers. Okay, so we're getting a ton of numbers. This is what we expected, right? It's going to run for 10 seconds, and it's going to print numbers not necessarily in order. Let me see if I can find some that are actually out of order. 9876, just kind of glance at it. Here's one. So we've got 20, 21, 22, 23, 30, 29, 28. So the reason that some of these aren't in order is because the threads do not get exactly the same amount of time, and the CPU doesn't exactly visit them in the same order whenever it's going through all the threads on your computer. So in this case, when we got, 22, 23, what was happening was the writer, the one that's putting things onto the stack, just put 7 things in a row before the reader got to do anything, and then it switched to the reader, which popped off the 30, then the 29, then the 28. So that's what happened here. Okay? So these will not always be in order. Generally they will be, but not always. Actually, we can see that here. Oh, right, because it'll only pop if there are 10 items on. So, of course, the first one to go is 9. Okay. But now, watch this. I'm going to make another reader. So we've got reader, and we've got reader 2. And we're going to start reader 2 as well. And we're going to run it and see what happens. I'm wondering what you guys think will happen. If you already know the answer, don't say anything. I want people to guess. I'm gonna go ahead and run it. Watch the console. We're gonna get some numbers, and we got an error. It's gonna keep running though. Let's check out what this error is. Actually, this error is gonna span multiple lines, and it's okay. Yeah. So what we're gonna do is we're gonna disable the console output so we can see the error. So we're gonna go into stack reader, and we're gonna comment this out, but we're still gonna pop. We still want to take the top item off, but we don't want to print it anymore. Now I'll run it so we can see the error. Alright, exception in thread. Now I'm not gonna show you what the exception is, but I want you to just realize what we've done. So the code that we had was this. This is the code we had. One writer, one reader, started both of them, and it went like 80,000 digits. That's how much it can do in 10 seconds. 80,000 digits. It went 80,000 numbers. I'm not running the Cray supercomputers. I can't do 80,000 digits in 10 seconds. So we have one writer and one reader. We started both. It printed out 80,000 numbers and then stopped. No problem. All we've done is added a second reader. Now let's look at that exception. When we add a second reader, we get this exception. We get empty stack exception. Let's see where this happened. Empty stack exception here. Okay, stack pop if you look at it. It's gonna load the job. Oh, you can't see it down there. Here, I'll pop it up right here. Oh, that's kind of small, but whoops. Removes the object at the top of this stack and returns that object. Throws empty stack exception if the stack is empty. Makes sense, right? But how can this happen? We're checking if the stack is empty right here. This code will only run if the stack is empty. Actually, that's not true. Okay, if this were a single-threaded application, this would be true. Okay? But in a multi-threaded application, here's what's actually happening. Say, I'm only going to talk about the reader threads, the ones we're looking at in this file here. We have 2 of them. What could happen, and it turns out what did happen, is thread A came here, and it said, okay, the stack's not empty, it's got one thing in it. So this returns true. Okay, it was not empty. So thread A makes it here. Meanwhile, thread B comes here at almost the same time, and it also sees that the stack has one thing on it. So now thread B says, oh, okay, this whole thing is true, I'm going to jump inside this if. So B jumps inside the if, so now they're both inside the if. One of the threads pops the top item, and then the other thread later tries to pop the same top item, which is of course no longer there. So these threads are actually running the same lines of code, not necessarily at the same time, but at the time we got this error, they were running this line of code at the same time. Actually, they were running this line of code at the same time. Okay, between this line and this line, both threads were able to get inside the if at the same time, while the stack was not empty. That's called, oh god, the word escaped me. That's called a race condition. When 2 threads are trying to do some operation to the same thing, and they happen to do it at the same time and cause an error, when they shouldn't be doing it at the same time. That's called a race condition. Now there are several ways to check if a race condition is about to happen. You have to do it manually, of course. Java can't detect it. But one way you can do it, and this is pretty common, is, alright, if the stack's empty, we're going to jump into this line of code. Java has a keyword called synchronized. And I don't remember, I think it's like this. We're going to get rid of the system out. Okay, that does look like how you do it. Maybe, maybe not. Hold on, let me try this. I think it's actually... What does it take? It takes an object. Okay, I can do it on the class object. Let's see if this works. Oh, but I have to do another if. I believe I have done this right. Let's run the main method and see if it works. It looks like I've done it right. We're not getting any errors, and it should say build stopped after 10 seconds. It does. Okay, after 10 seconds. So Java has this keyword called synchronized, and there are two ways to use it. One is to use it like this, where you treat it kind of like it's a function, as if the synchronized is the name of the function. The object that you send in, of course it's not, it's just the way that Java works. It's not actually a function, but treat it like it is one if we do something like this, right? So synchronized, and it takes a parameter. The parameter that it takes is an object. And what it will do is, as long as this object, it will assign this code, whatever is inside the synchronized block, to this object. This object gets a lock on that code until it's done running. While this object has a lock on that code, no other this object, it's kind of confusing because I'm using a class. I want to be as clear as possible because this is very confusing the first time you learn it. The parameter that it takes is an object, a reference, okay? When it calls this block of code, this particular object gets a lock on that code, meaning if this same object tries to call this block of code again, it will wait until all of the other threads running that code are completed. So in this case, I use this class, the stack reader thread class. So what's going to happen is, let's go back to this stack is empty. They're both going to say yes, so both of the threads come into this if block right here, right before the synchronized. Now, only one of the threads can hit this synchronized block. So one of them is going to hit this, and it's going to get a lock for the class, for stack reader thread class. So as long as any stack reader thread is running this code, no other stack reader thread can run this code. Okay, so this block of code can only be run one at a time because we put this synchronized around it and we limited this code to one per class. If I did just a synchronize this, I don't actually think this will work because we have multiple different threads. Yeah, we still get an exception. So that, whoops, wrong one. I'm in here. Alright. Are there any questions? Are there any viewers? Hopefully you guys are following this. This is a very confusing topic. The first time you learn about synchronization, multi-threaded, deadlocks, which I haven't talked about yet, that's the last thing I'll talk about, and race conditions, these things are, you know, they don't happen in normal life, right? They're not logical for the common, you know, they don't make common sense. But when you put them in the context of how threads work and how your CPU is constantly switching between them, it makes a lot of sense. It doesn't look like there are any questions, so I'm going to move on to deadlocks, but I'm just going to very briefly summarize one more time. Let's say we have two threads that jump into this method, or jump into this if block. We have two threads running this code at the same time, and they evaluate to true. So they're both going to get here right before the synchronized. One thread is going to go into the synchronized, it's going to check this, and it's going to get a lock on all thread readers. The thread reader class, or sorry, the stack reader thread class, this thing, the whole class is getting a lock on this code, meaning no other object of this class can run this code until it's done. So that's why this works, but when we get rid of these two lines and the matching brace down here, it doesn't work. We get an exception because multiple threads are allowed to be inside here. When you have a synchronized here, only one thread can get inside. The second way to use synchronized is to put it outside of an entire method. We can't really do that for the run method, but the way you would do it is, let's say we had another method maybe inside the thread class, private synchronized void wait for me, and we had some code in here. What we can actually do is we can actually just call this method, and we're guaranteed that only one thread can run this method at a time. That's the synchronized around a method automatically puts a lock on the class for that method. So that's the other way to use synchronized. This is more common, but there are legitimate reasons to use this one. I mean, there are good uses for both. Sometimes you need to make a method synchronized, and sometimes you only need to do it for a small piece of code. You don't want to do synchronized too much, because for Java to get a lock and release a lock actually takes a lot of time. There's a lot of overhead. It's milliseconds, but if you're looping through a million things, you do not want to have a million locks going on and coming off. Okay, you want to lock as little as possible, but preserve your program. You don't want it to error. So the very last thing I'm going to talk about today is a deadlock. And I have never written a deadlock before, so this will be a first time and I'll probably do it wrong. A deadlock is a bug where one thread, let's say we have thread A and thread B. A deadlock is where they get into a state where thread A is waiting for thread B to do something, and thread B is also waiting for thread A to do something. So they're both just permanently waiting for each other, and of course nothing ever happens. That's a deadlock. Let's see if I can create one. We're going to have a stack reader and a stack writer. And what we're going to do is, let me think, how are we going to make a deadlock out of these? So we've got a stack. We're going to wait, we're going to run for 10 seconds. Oh, here's a good way to do it. While stack.size is greater than, this is the stack writer, while it is greater than 10, we're going to push numbers. Okay, so we're going to actually populate it beforehand. And then the reader will be, yeah, we don't need this anymore. Did I get rid of that over here too? Nope. Go away. You don't want to have useless code in your program. While stack.size is less than 20, we want is stack empty. We're not going to use the synchronize because we're only going to have one reader. I'll just get rid of that and format it. Oh, we don't need this stack empty either. And we are going to print out this one. Oops. So I believe that I have created a deadlock situation, but we need to change one more thing. We need to populate the stack a little bit, because if it starts at 0, nothing's ever going to happen. So 0, it doesn't return a stack. I can't do that. Let's just loop it. Copy-paste was going to be the lazy way, but we'll do it the correct way. Alright, so we're going to populate the stack with the numbers 0 through 14, which means this one's going to start at 15. And that one doesn't need to start anywhere, because that's only reading items. Alright, so the writer and the reader are both going to run for 10 seconds. Oh no, they're not going to run for 10 seconds. They're going to run forever. Okay, both of these threads are going to run forever until... Actually, no, they'll run forever anyway. But what we should expect to see is we should see a constant stream of numbers printing on the right. Okay? And eventually, if we wait long enough... Oh, we didn't have to wait that long, did we? I must have done something wrong. Hold on. Did I reverse these? This is the writer. While it has more than 10, we're going to push. While this has less than 20, Oh, we're gonna get rid of this. That's what was going on. Alright, now let's try it. That's still not right. Let's see. Even though the stack is empty when we give it to them, it's the same object that we're referencing. So this is not a problem to populate it after we've created the threads. That's not a problem. So the stack will have 15 objects in it. The writer, I want it to add numbers while there are more than 10. Let me start the reader first. Because it may be that the writer is just adding too many numbers. Actually, that's a good idea. Let me do this. And then the reader is going to say popping plus stack pop off the stack. Oops, one quote too many. Okay, now it shouldn't matter what order I put them in, because we'll see the correct results. The reader is just not doing anything. Did I modify this correctly? While the stack size is less than 20, we want to read when it's less than 20. We want to write when it's greater than 10. Oh, I did it. Let me think. Creating a deadlock is hard when you're trying to do it on purpose. When you're doing it accidentally, it's actually a lot easier for some people. I will not name names. Let me see. I want to get them to a state where the writer, while the stack size is less than 10. Creating a deadlock on purpose is really hard. Like, in my head, I know the math behind what I want to do. I just don't know how I'm going to do it with 2 threads. Because this is going to add forever. Yeah, but I'll just limit it. What about greater? Yeah, 10's fine. And stack size. Actually, here's what I'm going to do. I'm gonna make this number static on another class. I'll put it on the MyMath class. I'm not gonna give it an accessor. N equals let's do 100. Public static int n equals 100. Int n equals 100. We're gonna have a problem if they try to write and read at the same time. Actually, it doesn't matter. And then it's going to be mymath.n. mymath.n++. And then the reader is going to do stack pop off the stack mymath.n-. So now we've got the same number going up and down. And actually, we're going to start it at 15, not 0. Oh, it was at 100? We'll start the stack with 100 objects on it. 100 objects. Let me think, make sure this is correct. While it's greater than 200. Oh no, let's do 50. What am I doing? Hold on. We've got n. While n is greater than 110. Let's do 100. Let's do 200. Why not? While, oh, mymath.n. This is a better way to do it, I think, if I spell it right. Mymath.n is greater than 200. It's going to keep incrementing. And the other one, while mymath.n is less than 100 and n is greater than 0, because we do not want to get an empty stack exception. Mymath.n. So I think if I've done everything correctly, this will run for a little while, but eventually it'll stop. Actually, that's not going to work either. Wait, will it? While n is greater than 200. Oh, we have to start it at a higher number, don't we? Let's start it at 0. And in this method, we're going to add 300 to it. While n is less than 300, stack add mymath.n++. Alright, so what's going to happen is I'm starting n at 0. I'm going to add all the numbers from 0 to 300, and n is going to become, well, actually 299. Our reader is going to only care when n is less than 100, or n is greater than 0. Sorry, and n is greater than 0. Stack writer will only care... Oh, that doesn't make sense either. Hold on. Oh man, writing a deadlock is hard. I need to find a way to write two threads where they will wait for each other. So I want stack writer to wait until the number is in a range. I want stack B to wait until it's in a different range. I actually have no idea how I'm going to make a deadlock. Writing bugs is hard when you're doing it on purpose. It's much easier when you're actually trying to make good code. Unfortunately, I don't have any good multi-threaded code that I need to write. I need two threads to wait on each other. Maybe I should have ended this video like 20 minutes ago when I was about to write a deadlock. I'll probably do that in editing. I really wish that I could write a deadlock. I'm too good. Let me think for a minute, because I really want to. Why does this song have words? Next. So let's see, we're adding n to the stack. We are going... Okay, what if I make n go up by 1, and I have the other thread waiting to divide it by 2, but the first one will only add to 1 if... Okay, while n is even, this is what I'll do. While n is even, oops. While n is even, I'm not even going to use the stack anymore. I'll send it to them just so I don't have to recode it. N plus equal 3. So whenever n is even, we're going to add 3. And whenever n is prime, we are going to... Why is it giving me error? I always forget to put the class in front of it. It was a long day at work today. We're going to, let's see, while it's prime, we're going to make it even. Alright, so this should hit a deadlock pretty quickly. I wish I could do one that would take longer. So let me think. 300, 303. Yeah, that'll work. Actually, no, it won't. Let's do 98. I'm trying to think of a sequence of primes where this pattern will work for a while, and then it'll stop. Alright, so let's do... n is that adding 1. And then I'll do down here, n is that adding 3. So while n is prime, we're going to add 1. And while n is even, we're going to add 3. So this will eventually stop. I believe. We don't need this stack thing. We're going to start n at the number 1. Yeah, sure, why not? Let's see what happens. Oh, it just finished. Oh, it's because this is going to run forever. I need to make this a while true, and then do a synchronized of this. If that synchronized this. Same thing we did before. This is going to work. And we're going to put this code in here. And we're going to do the same thing on the other thread. While, cut this out, one more, true. We're going to do a synchronized, oh wait, if that, I need to put a second if check in the other method. Synchronize this dot get class. Oh wait, I don't need to synchronize that. There's only one thread of each type. You only need synchronized when multiple things are trying to do the same thing, but these are not trying to do the same thing. Although they might modify the number in you know, out of order, so we might get some interesting printout. So if it's even, then do that. While true, if it's prime, then do that. All right, let's see what this does. All right, so here we go. Now notice the program is still running because I have the terminate button right here. So we got n is 1, we're adding 1. N is 2, we're adding 1. N is 3, we're adding 1. N is 3, we're adding 3. Okay, so we already have a race condition right here. But that's not the reason this is infinite looping. N is 7, adding 1. Okay, goes to 8. N is 8, adding 3. Wait, which one adds 1? The prime? Okay, the prime adds 1. The if it's even adds 3. But notice it was 3 here and it added 3 anyway. So this is an example of a race condition where two threads are hitting the same code at the same time. But if it's even thread got to the system out, the other thread had incremented it. So n was 2, and then the other thread jumped into it and saw that n was still 2, and it tried to add 3. So that's what happened here. But anyway, we got to n is 12, we're adding 3. We actually don't know what n is, but I'm guessing it's 13, right? No, it can't be 13, it's 15. It's an odd number that's not prime. So this thread is waiting for n to be even, and this thread is waiting for n to be prime, and it's neither of those, and it'll never change. This is a deadlock. This is kind of a crude example of a deadlock that took me like 10 minutes to think of. There are actual examples where deadlocks happen in real life. For example, if a program is trying to read a bunch of different files at once, and it needs some files to read the others, you can actually get a file deadlock that way. If you're waiting on network connections from different places, if your company has services that go back and forth and you need one service before you get the other, and if it's really convoluted, then you can get deadlocks on waiting for network data. There are all kinds of deadlocks you can get. What I wanted to teach you though was how threads work. I hope you remember by this image right here. Each of these processes on your CPU is a separate thread, it's a separate process. Your CPU switches between them constantly, faster than you can see, way faster than you can see. And it just runs a little bit of code in each of them every time your monitor refreshes. Okay, so every frame that your computer shows, it has run a little bit of code in all of these. If you create lots of threads for one program, that program gets extra attention because there's more of them. And that's the only reason. And be careful when you have multiple threads trying to access the same value, because you can get race conditions where two threads think they know the state of an object, but one thread changes the state after the other one has looked at it, so they end up jumping into the same loop at the same time, or a similar loop at the same time when they shouldn't. This is a race condition. Or a deadlock where two or more threads are waiting for each other to complete, and because of that, neither one of them completes. Okay, so that's all about multi-threaded threads. That's all about multi-threaded programming. And as we saw with the first thing, with calculating 100,000 primes, having more threads actually does speed up your application by a significant amount. And if you're really clever about how you distribute those numbers, you can get really, really efficient results. Somebody else asked a question a long time ago. I don't know if he's still here, but his question is good and I never answered it. What's the highest number of threads you should use for the best times? Well, that really depends on what you're doing. I mean, there is no ideal amount of threads in a general case. How many threads you create has to do with what your program does, how much data it's using, how many other processes are on that CPU. It has to do with a lot of factors. And it's up to you as the software designer, as the engineer, to try different things and try to find the most efficient setup for how many threads you should have, what data you should give them, or what data they should process through. It's really up to you to find the most efficient solution, if you want the most efficient solution. I have some code. I hope this is updated. It may not be, but I'm going to look anyway. It's in here. Oh, this is not updated at all. This is not updated at all. Okay, this is non-multi-threaded code. This is an actual program. It's actually a game, but it won't work. Or will it? Maybe it will. Do I have JMonkey on here? I should. Let's see if this works. Failed to find JME system delegate. Ensure either desktop. Oh, missing class path, I guess. Whatever. Alright, so it's not going to run. But this is a universe simulator. What this code does is it generates a bunch of particles, basically. Each particle has its own gravity. They're given initial velocities in a random direction. Where's my simple? When I create a galaxy, I'm giving it a mass, I believe, and I'm giving it a velocity. It's been a while since I've done this. And I just add them to a list. And then when I loop, I calculate some gravity. This is the gravity, right? Oh, this is the gravity thread. Anyway, I'm calculating all the gravity that they generate from each other. Well, if I'm generating a couple thousand particles, how many was I making here? Only 400? That's not a lot. But if I was generating like 2,000 of these things, and I had to update 2,000 particles times 1,999 other particles to calculate, gravity, that's a lot of calculations. This is not the most recent version of the code. This is actually the terrible code. The most recent version on my laptop uses multi-threaded techniques. I have different threads that handle different amounts of these particles. So I have one thread that handles about 1/3 of them. I have another thread that handles about 1/4 of them, etc., etc. And I was able to figure out by a little bit of math and a little bit of trial and error not only how many threads should I make, but also how many galaxies should I put in each thread. So it's really up to you to determine what's the most efficient way to do it, how many threads, and how much data should they have. A really visceral example, that was not the right word to use, a really realistic example, one that's really easy to wrap your head around, of multi-threaded technology. If you've ever heard of the at-home series of apps, like Folding at Home, or what's the NASA one, the SETI at Home, those are cloud computing services where if you download it, your computer, while your CPU is not doing anything, if you're watching like a YouTube video that's only maybe 1/5 of your total CPU power, the Folding at Home or the SETI at Home, and there's a lot of them now, but they will run some calculations as your CPU has some free time. Okay? And think of each different person's computer as a different thread. That's exactly what it's doing. If 100 people download this Folding at Home app, then the Folding at Home project can calculate 100 times faster, because that many more people are running it. They're splitting up the giant amount of data that they have, that they've measured through, or actually they haven't measured it, they're generating it. They're splitting up, they're distributing the math. And each person's computer is getting a different set of data, so it can all calculate really fast and concurrently. So the Folding at Home, the SETI at Home, there's a bunch of others that I can't remember the name of. Most of them end with at home. If you download that, your computer acts as a thread for that online service, more or less. So that's a really good example of an application, a real-life application of why you should use threads. If I haven't already convinced you with the fact that your programs will run a lot faster. I used 4 threads, my program ran twice as fast. The original Prime one. Alright, well nobody's talking or asking questions, so I'm gonna stop. I hope you guys learned a lot. I hope you weren't too confused. And I'm sorry about the long wait. I know it took me like 10 or 15 minutes to actually code a deadlock. But coding deadlocks is hard. It's not often that you'll have 2 threads that wait for each other. It does happen, but it is not the most often problem you'll run into. And usually when you run into that problem, it's a very easy problem to detect and fix. You're very quick to know what's going on. However, race conditions are not easy to find. Okay? So when you're programming in multi-threaded mode, when you're in the zone, right? You want to think about race conditions when threads might be accessing the same data at the same time. That's what you don't want, because if that ever happens, it might take you forever to find out what's causing a problem in your program. And the problem might not show up for a very long time. I mean, in this case, it waited until we got to n equals 15. It's probably going to do that a lot. Okay, well that time it stopped at 4. Actually, it stopped at 5. So n equals 4, adding 3, but the other one's adding 1 when it was already 4. So now n is 5. Wait, that doesn't make sense. What could have happened? They deadlocked. What value of n would make them deadlock this low? Let's see. N is 3, adding 1. Okay, it's 4, adding 3. That would make it 7. But the other one would have made it 5. Or 8. 5 is prime. So is 7. I wonder what happened. I wish I could like look into it and see what happened. Maybe I can. I'm gonna debug it every time. This is gonna be cool. I want to see what number generated that. I know. Okay, here it got stuck. So let's take a look at the reader. Let's see what number we're looking at. Where is it? I'm looking at this one. N. It's 4. So it's not prime, and the stack reader, what happened? Did it die? I don't actually know where this other thread is. This is the reader. Oh, this is the writer. I need to switch over. Okay, I got here, and n is 4. It should go in here then, right? Oh, that's interesting. Why was it waiting on the other one? Did I just find a... How much have I covered since I started this series? I'm pretty new to this. I figure it might be a good way to learn. I have covered everything from the very basics. I'm glad you're here, and I'm glad you find this interesting. I actually tried to write a bug on purpose, and it took me 15 minutes to figure out how to do it. Because multi-threaded bugs are not things that you write on purpose ever, so I don't have a lot of practice. I can probably write them by accident like a pro, but I just found something very interesting where this thing printed down to n equals 3, and then it didn't print for a while, and it only printed when I started debugging. There must be something in Java that's like caching the value of n or something. There's something going on inside of Java that caused it to do that. Because I just debugged and ran through the thread one at a time and it kept going. But now it is actually stopped because n is 15, which is neither even nor prime. So they're both waiting on each other. This is a true deadlock. But every once in a while, it might get past that deadlock and it'll deadlock later. So deadlocks are unpredictable, but if all your threads just stop, that's an instant red flag to know that you have a deadlock. When your threads hit a race condition, you might not know for a minute, you might not know for days, you might not know for months. One day your program will just break and nobody can know why. So when you're coding like this, when you're coding multiple threads, keep in mind that race conditions can happen. That's probably the hardest kind of bug to find. If you learn nothing else, remember what race conditions are, what causes them, two threads accessing the same thing at the same time. Make sure you synchronize it, or you do some type of checking to make sure that can't happen, because that will take up way too much of your time. Okay, it costs companies a lot of money when that happens, because of the manpower spent trying to fix the program, when nobody knows what went wrong. But anyway, I have successfully written my deadlock. And that's all I had to go over. It took like 15-20 minutes longer than I wanted to. But Gilga Grill, he said it's interesting and how much of the series have I done. I've done everything from the very beginning. The first video is Java syntax, like how to write a basic program that just says hello world. Okay, that was the first video. And every video since then has been progressively more advanced, just a little bit. If you watch from the start up to here, I sprinkle in a little bit of high-level stuff every now and then, but I try not to put too much too fast, because I don't want to overwhelm new people. It's very hard to learn your first language, but once you learn one, the others become easy. Anyway, I'm glad you guys enjoyed it. I hope you all learned something, and tomorrow I'm actually taking a vacation. So what's up next now? What's up next? I actually have no idea what I'm doing after this. That's really great to hear. Gilga Grill is commending my ability to explain things, which actually makes me feel really good, because I'm a little bit self-conscious about how I explain things. You may have noticed sometimes I will like pause in the middle of a sentence to think about the rest of the sentence. That's just how I speak when I'm thinking. So I'm really happy that you guys find this easy to understand. And to Gamer Coder, what am I doing next after this video? I'm probably just gonna troll around YouTube for a little bit, because it was a long day at work, you know? And I'm pretty tired. I might play a game. I don't really know. But I've been going for an hour and 40 minutes on this video alone. So this will be it for learning to program. A series about the Spring framework. You're picking on me. I don't know if you were here. You probably were, which is why you said it. I do not like the Spring framework for many reasons. And maybe I will talk about those reasons in a different video. For those who may not know, which is probably most of you, because before I got this job I didn't know what it was, the Spring framework is this giant library of what they call features. The primary motivation for Spring is to get rid of constructors in your code. Basically, you can set up a bunch of XML files, which they have some cool stuff in them that allow you to create mostly singletons. It's designed to create your singleton objects for you automatically so that you don't have to. And the reason that this is useful is, let's say you're writing a like an eBay type of thing, or not eBay. Let's say you're writing let's say you're a bank, okay, and you're going to write a program for your bank where your users can that's a terrible example too. Let's say you're a credit card company. Third time's the charm. Let's say you're a credit card company, where you have to write some programs where other companies can communicate with your services to charge people money, right? When someone pays at the grocery store with a credit card, that grocery store has to contact MasterCard electronically, or Visa, or whatever it is, and they have to say, I want to charge this person $80, they bought stuff. Okay? Spring Framework is really good at setting up your database connections so that if you're that credit card company, you have the side of your program that interfaces with the grocery store. So the grocery store says, I want to charge $80. And then you have a separate set of programs that access your databases. So they go in and they say, does the person have $80? If they do, are there any locks on their account? Are there any holds? If they don't, then you send back, okay, you've charged $80. And so Spring is really good at setting up things like database connections, which you only need one of, right? You only need one database connection for each database. It's really good for other things like for people logging into websites. Spring can track their login. So each person's login is linked to them. So Spring is really good at setting those up and keeping track of those. It turns out I'm going to talk about Spring during this video when I didn't want to. But the thing that's bad about Spring is that over time they added too many features to it. So Spring isn't really a library about instantiating things. It's a library about doing a little bit of everything when you don't really need a little bit of everything. For example, we're writing a new program right now at work, and I'm trying to think of a really good way to explain why Spring sucks. Okay, let me say it this way. There are some really good features in Spring, like Spring MVC, a model view controller. Spring can actually intercept people's web calls. So if somebody's trying to visit your website, normally what you had to do in the past was your web server was basically running what we call a REST server. It receives GET commands and POST commands, and it sends back data. Spring lets you intercept those commands and do stuff in your Java code, and then your Java code can send back a website, or a page, not a website, a web page. So Spring lets you intercept and change people's data and then send data back to them. So that's a really good feature of Spring. But it comes at a cost. Spring, it comes at a lot of costs. One of those costs is the configuration that you do, the initial configuration in XML, and now they have annotations as well. The configuration sometimes takes more time than it would just to write your own Java code. Like, getting rid of all the constructors in your code usually isn't worth it. Sometimes it might be if your constructors are really weird and you need to have like different configuration files for different environments or something like that. For example, we set up different database connections on our test servers than we do for our live servers, right? So Spring's good at things like that. But for a lot of cases, Spring is actually not useful in setting up your objects. But probably the biggest turnoff for me is when Spring creates an object for you, it doesn't actually create your object that you wrote. It creates what's called a proxy object, which kind of exists and kind of doesn't, and if you're trying to debug it, you can't. You just can't. You can't look inside of Spring's proxy objects. It just doesn't let you. So you may have a bug in your program, and that bug may be very difficult to track down just because Spring doesn't let you look at its proxies. That's probably the biggest turnoff for me, is sometimes you just want to know what's in your objects, and Spring doesn't let you. I mean, there are a lot of things I could say about Spring. There are some good aspects of Spring, but I think it's overused, and I think it's overhyped. It's overappreciated. There are a lot of useless features in Spring, and most of the features in Spring are not connected to each other in any way. But there are some good features that are usable. Anyway, I didn't really want to talk about that, but maybe I'll put it as a bonus when I highlight this. Alright, well, I don't know what I'm doing next. I'll play a game or watch YouTube. But anyway, I hope you guys did learn something. I will not be streaming over the weekend. I'm taking a little mini vacation. So I will see you guys probably next Monday. Tracking bugs becomes a game of hide and seek where you aren't allowed to open some of the doors. I would say that's a pretty good analogy. Yeah, Spring, you can debug through like the lines of your code, but you can't actually see the objects that Spring has created for you because they are not your actual objects. Another thing is that I didn't mention, but it's very quick. Spring has a ton of overhead. If you're running an application that needs to be fast, I mean, at my company we don't, because we write websites. You know, if a website loads in less than 2 seconds, we're fine. A little overhead, not a big deal. But if you're writing like a scientific data analysis tool, you do not want to use Spring, because it populates your stack so much. Like, every method you call gets intercepted by like 10 other Spring methods. It's just a huge amount of overhead. So if you're running an app that needs to be fast, you do not want to use Spring at all. It uses way too much of your CPU time and your memory. If you're running a website, then Spring MVC is fine. But anyway, I've already talked too much, and I've said that like 3 times. So I'm gonna go. I'm glad you guys enjoyed it, and Gilga Grill, really, thank you so much for your comment. I'm glad that you find what I say easy to understand, because that's probably the #1 thing I'm going for, is I want to teach people who are new or who have not done any programming at all, and you seem like you're in that category. So it means a lot to me that you find me easy to understand. Alright, well, I'm going to go. I will see you guys next week. Have a great weekend, everybody. If you're in the southern hemisphere, I envy you because it's getting cold up here. But have a great weekend, everybody. And thanks for watching. And that's my Chrome window.